Let's apply what we've learned now to our control framework. So when we say framework, we know that in general, our process is changing in time in respect of its state variables. So these y values, this might be a vector of concentration or temperature or pressure. So all our states are described in the vector y. And we know also that we have some elements that we can control, for instance, flow rates and so on. So from our material balance or momentum balance or energy balance, we have some relationship between our state variables and the variables we can control, like flow rates. So we know we have this kind of rule behind everything. And we've also shown that we can do Laplace transformations of each of the terms. So whatever the equation is, if we transform the derivative, we'll get an S times capital Y, and then we can transform the Y's and the U's, and eventually we can summarize the relationship as a G here. And just as an example, let's do a simple first order case. So we've got dy dt is ay plus u. In fact, we have done this already. So if you look a couple of videos back, we did this, but anyway, let's just do it again. So the transformation of dy dt is sy, and then the transformation of this is ay, and that's a u. And there we recognize that we've got y's on both sides, so we can group that out as a y times s minus a, and the u is left over here. And then our transfer function is defined as y divided by u, so that's going to be a 1 over s minus a. So now in the context of the previous video, we were concerned about the poles of our transfer function. So we can see a pole is where s equals a. So a criterion for us is that a should never have a real, a real part that is positive. So in our system of equations, a must be negative if it's a real number. And we can see that directly here. So we know that in an equation of this form, if a is ever real and positive, then this goes off to infinity. But it's not always the case that we have an easy equation like this. In some cases, we can only obtain the G version of the equation. So it's useful now to have this criterion for the Laplace domain. If we have a second order system of equations, so let's take this general form. So it's second order, so d2y dt squared is a dy dt plus by plus u. So it is the most general form of a linear equation, which is second order. And to solve this, we will convert this to the single second order equation. We can convert it to two first order equations through these definitions. So the first definition here is a little silly. It's just saying let y1 equal y. And the second one says let y2 equal dy dt. So if y1 equals y, we can say dy dt is also equal to dy1 dt. And so we have here dy1 dt equals y2. So we can regard that as one equation. And then if we look at our original equation here, what we are trying to do is get rid of the second order term. And we can recognize that d2y dt is the same as ddt of y2, right? If we take the derivative of y2, then because y2 equals dy1 dt, then the derivative of y2 will be d2y1 dt squared, which is also equal to d2y dt squared. So this d2y dt squared can be replaced by dy2 dt, and that's exactly what we do here. Then continuing with that, we can also recognize that here, instead of writing dy dt, we can just replace this with a y2. So this is an ay2. And then here we can't use a y2 because the order isn't high enough. So here we can just write this as by1. And then the u, there's no reason to do anything there. So now if we look at these equations, we do have two first order equations. They are coupled equations because you can see dy1 dt is influenced by y2. So what happens when integrating this equation will influence what happens here. And similarly here, the rate of change of y2 is influenced by the values of y1. So these are coupled ODEs, which is fine. We can always deal with, we can always integrate them simultaneously. But we have done the main thing, which is convert a single second order equation into two first order equations. And we can use that then to infer the transformation function, or the transfer function. And so to do that, we can transform the first equation. We can Laplace transform it. So we recognize this as S capital Y1. So S capital Y1, remember the derivative is just S times the transformed variable. And then this one we'll just leave as a Y2. So that's simply the transformation of this equation. And then if we transform this equation as well, again, we can write this as SY2. So that's what we have here. And we can write this as AY2, that's there. And this is BY1, that's there, and the U. So that's the Laplace version of this equation as well. And then we would like to get rid of this Y2. So we do have this equation. So wherever we have a Y2, we can replace it with an SY1. So if we replace this Y2, then it's going to be S squared Y1. So that's there. This Y2, we get SY1, and the rest stays the same. And then looking at this, you've got Y1s in 3 of the terms. So we can just group them all together, taking some terms across here. So we've got that, and the U is left over there. And then we've got the transfer function. We always want Y over U for the process transfer function at least. And so in this case, again, because lowercase y equals lowercase y1, then we can say uppercase y equals uppercase y1. So we can just write y over u equals y1 over u, which we can see is going to be 1 over this. So that's our transfer function. And if we look at this denominator, we recognize this simply as a quadratic equation. And so that's going to have 2 roots, R1 and R2. Okay, and so this is the standard form now of our second order process. So all second order processes are going to have this type of transform, this type of this form for the transfer function. And in fact, if we compare with the first order case, if we go up here, for the first order equation, you can see we had something similar, 1 over S minus a constant. So here we have a second order case, 1 over S minus R1, S minus R2. And if you keep doing this, right, you could do this for third order and fourth order until we're well enough satisfied, or better if we prove it by induction, which I haven't done here. But if we have an nth order system, then we can show that the the transfer function will have that form. So 1 over S minus R1 up to S minus Rn, right? So for an nth order system, that's what we have. And we can see here that our stability criterion would be that all these roots, all these R's must have negative real parts if this process is going to be stable. So hopefully that gives us some confidence in transforming any order of system, and it tells us what to look out for, how to analyze for the onset of instability.